Hi, everyone. My name is Abdullah. In this presentation, we're going to take a short detour into a different cluster orchestration system that you're probably all familiar with, which is Kubernetes, and our efforts to improve the batch experience in Kubernetes. Next slide, please. So I work for Google, specifically on the Google Kubernetes engine, which is the managed Kubernetes service that Google offers as part of its GCP suite. My team mostly focused on open source work in Kubernetes in two special interest groups, specifically scheduling and apps. As you may know, in Kubernetes, we have these special interest groups that operate under like open governance model. They set, feature requests, implement specific features in different components of Kubernetes. Our goal in general is to improve the batch experience in Kubernetes, my team's goal. And specifically in, again, as I mentioned, in scheduling and in the apps segs. Next slide, please. Before I explain what we're trying to do in OS as Kubernetes, I would like to give a quick intro into the Kubernetes architecture. Kubernetes has a declarative API, meaning that generally the way that users interact with the cluster is that they declare the state that they want the cluster to be at. And they do this by creating resources in a storage called HTCD through a service called the API server. So what the users does is the only thing that they are able to do is to basically communicate with the cluster through the API server. These resources, once created on HTCD, there are other controllers running on the cluster that tries to drive the system or the cluster state into the state declared by the resources stored in HTCD. Here in this slide, I'm showing the main two types of nodes that we have in Kubernetes: the master, which runs the controllers that I mentioned, and the nodes, which run a node agent called kubelet that actually creates the processes that executes the workload, and we call them pods. The two main components that I'm going to talk about here and later in my presentation are the scheduler and the controller manager. And those are the two components that I mentioned that are related to the two special interest groups, SIG scheduling and SIG apps. So as I mentioned, users create resources on the API server. Controllers, like for example, if they create a deployment, the controller manager has what we call a reconciler. Sees that there's a new deployment being created. The deployment, for example, requires creating multiple pods. That reconciler, what it will do is that it will create pod resources, again, on the API server, through the API server on HTCD. Once that happens, the scheduler watches for resources being created on HTCD, specifically pods. It will see that these pods are new. They don't have a node assigned. What the scheduler does is that it will assign a node to these pods. Now, the kubelet will watch for pods assigned nodes, a node name equivalent to the node name that the kubelet is running on. When it finds a new one that is not yet running on the node, it will create the pod. So that is the sequence of events that happens in Kubernetes. As I mentioned, there is usually no direct interaction between these components. Everything goes through the API server. All controllers are watching for state changes in HTCD. When a thing happens that doesn't equate the state of the current state of the cluster, they will try to drive the cluster state to match that of HTCD. So it's basically like eventual consistency, so to speak. Next slide, please. Now, specifically to jobs, I want to give a quick intro into how Kubernetes currently support creating batch jobs in Kubernetes. And job is one type of what we call app. Like there are other apps, like for example, services, deployments, replica sets. Job is the type that is specific to support batch workloads. And it has some similarities to how we create class adds in HTCondor. On the left side, I'm showing a job resource. In the job resource, you can specify or you can declare, for example, the template. The template basically, in the template, you specify the set of containers that you want to create. And for each container, you specify how much resources they need. In the requests field, you specify the minimum amount of resources that needs to be allocated to the container. And this minimum amount is taken into account when we match with nodes, basically using the HTCondor terminology. Basically, the scheduler will try to find a node with a minimum of this much resources in the node to assign the node to the pod. The limits specify the upper limit of how much resources the pod or the container can use on the node, if there are free resources on the node that are not being used. This is again equivalent of something similar to the way that we declare these resources in HTCondor, like request CPUs or request memory. We have also other primitives like node selector, which allows users to say, okay, I want these pods that are being created by the job controller to be allocated only on nodes with specific labels. For example, a node type E2, VM type E2 micro in GCP. Now, job, as I mentioned, is a higher level resource. When you create the job, you specify you can have one or many pods being created, and those pods that you're going to create, you can specify the parallelism, like how many can run at the same time, and completions, which is how many eventually should run to declare the whole job as completed. I will talk about a little bit more about that in the next slides. Next slide, please. So here I'm going to take you step by step how we're going to create like the pods of a job. So next step. So first the user creates the job, as I mentioned. Next. The controller manager will basically see that the job has been created. It will create the pods. Next. And then as I mentioned, it will assign pods to specific nodes. Next. And then Kubernetes will get these notifications that those are pods from this job being created, and it needs to run on these respective nodes that the scheduler assigned. Next. And then we'll start the pods. Next. And then once the pod finishes and exits, it will update its status. Once there are a number of specific pods that is completed, which is declared by the completion parameter on the job resource, then the controller manager, the job reconciler and the controller manager will declare that the job has finished. Next slide, please. Okay, so that's like quite a bit of background, and this is the basic things that Kubernetes support in the batch world. So the problem that we're trying to address here is that support for batch lagged in OSS Kubernetes. Most core Kubernetes components are pod-centric and not quite compatible with batch workloads, where, for example, as I described, everything happens at the pod level. The scheduler assigns, makes resource assignment decisions based on at the pod level, not at the whole job level. Even auto-scaling happens at the pod level. So that is not quite compatible with how batch workloads, with some of the requirements of batch workloads, where you want to allocate resources for the whole batch job rather than the individual replicas. The other problem we're trying to address is that we have a fragmented Kubernetes batch ecosystem. Now, to solve these problems that I mentioned, others have created custom controllers and custom job APIs to fix these gaps. And that led to a fragmented batch ecosystem. Like users, for example, when they want to create a job, if they installed, for example, Volcano, which is a batch scheduler, then they have to use the Volcano job API. Same thing with Kubeflow or Spark operator. Everybody has their own like job API with their specific semantics. Next slide, please. So we're trying to tackle these two problems. Specifically, we're trying to enhance the Kubernetes job model so that it's easy to use for simple workloads. You don't really need to build anything custom on top of Kubernetes to address simple use cases. And for more complex workloads, we want to have the job model as center of gravity. We don't want custom controllers or custom orchestrators to resort to creating their own job model. We want them to make the Kubernetes core job model as a building block and build on top of that. For example, if they want to create an MPI job, then the core job model that we have in Kubernetes should suffice to build that rather than creating everything from scratch. Next slide, please. In this slide, I'm talking about like the first thing that we're trying to address, which is enhancing the core job model. What we did recently is we introduced support for indexed job semantics. And the problem the index job solves is running large-scale parallel jobs that currently in Kubernetes requires setting up a message queue. With index job, now you can statically partition the workload. Think about like Monte Carlo simulations, embarrassingly parallel applications. You don't really need to create a message queue for pods to know which part of the problem that it needs to, of which portion of the job it needs to solve. The second enhancement that we introduced is a robust tracking of job completion status. As I mentioned, when the job completes, it declares its status on its CD. And when it does so, the job controller watches for completed jobs, for completed pods, and only then it declares the job as completed. Until recently, all these pods that completed should continue to exist on its CD until the whole job finishes, and that was not scalable. So we introduced a new algorithm to not require that. And finally, we also introduced automatic job objects cleanup. As I mentioned, all these jobs that you're creating, those are resources stored in its CD. And then we introduced new mechanisms to allow users to declare for how long this job should continue to exist. Users want the job object to continue to exist because they want to check, like to debug and check its status. But at some point, those are not useful. You could delete them after, for example, moving them to some other like external database. Next slide, please. So here, like a quick dive into parallel execution for jobs. So as I mentioned, until recently, you had to set up a Rabbit MQ kind of thing, like work queue. When you create the job, basically you decide how many pods are running, and then each pod will pull from the queue the next work item. Next. Now the new feature we introduced with index job, this is all statically partitioned. Each pod that the job controller creates will have an environment variable with a unique index. And so each pod that runs knows implicitly which work item it needs to work on. Next slide. And this is something, we can do something similar with HTCondor using like Rs and Q item in. So that's here I'm showing like how we can do something similar with HTCondor, similar semantics to the index job. Next slide. Now here I'm discussing like how we're addressing the second problem, which is unifying the ecosystem. So what we're proposing is hooks in the job model to allow higher level orchestrators to use the core job API as a building block. So the first one is managing the job as a single entity. What we added a flag to the job to tell the job controller whether the job is suspended or not. The idea here is that users would create, for example, jobs in a suspended state so that the job controller doesn't create the pods right away. and then an external component that has like a job level semantics will decide to unsuspend the job when it sees fit. For example, think about like a job queue controller. Also, it allows implementing preemption semantics at the job level. While the job is running, if for example, decided that this job doesn't have enough, should not have enough quota, we suspend the job and basically we're preempting it. We've introduced three other hooks. The first one is defining scheduling and provisioning properties through what we call like a job class. We define also job grouping so that we can implement batch jobs such as Spark or MPI that requires two types of pods, for example, the driver and the workers. And finally, also, we introduce a new hook that allows these higher level controllers to control which pods needs to be deleted when scaling down the number of pods backing a job. Next slide. So here I'm just doubling down on the first hook here. As I mentioned, this is similar to the first slide that I introduced, how the whole thing works in Kubernetes. The box in the orange could be like a custom job manager that decides when to unsuspend the job. When it unsuspends it, then the rest of the workflow remains Kubernetes native, core Kubernetes native. A custom controller doesn't need to create the pods or do anything else like monitoring job status. All of that will continue to be managed by core Kubernetes. But the custom job manager will only make decisions at the whole job level. Next slide. And so in summary, the Kubernetes community is investing more in batch. We know that historically Kubernetes focused on service workloads. We're investing more and more in batch. And our goal, my team's goal is to help unify the Kubernetes batch ecosystem around the core API model so that users don't feel torn between and have different experiences. They can start from a simple experience using the core features that Kubernetes support, and then they can easily have a ramp to a more complex setup. And by that, I have, this is the end of my talk, and I can have some questions. Tom, can you go to one more slide? One more. And this is a shameless plug for HTCondor support on Google Cloud. Feel free to reach out to Tom with regards to that.